listening to Würth Elektronik's What's Up, a radio podcast where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Würth Elektronik specialists who are going to shine a light on our topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast. In our introduction, we always mention that we are checking in with leading industry experts and Würth Elektronik technical specialists, and today that is exactly what we are doing. This podcast comes from a joint webinar with Würth Elektronik and onsemi regarding 25 kilowatt bidirectional fast DC charging. Our first speaker will present the basic block diagram for building a 25 kilowatt DC fast charger and the design for building a complete system, along with specifications and onsemi components used to build the charger. In the next section, the second presenter will discuss power chokes specifically designed for use in active PFC circuits. So in combination with the active boost PFC circuits, these chokes achieve high efficiency and a power factor between 0.90 and 0.99. The AGDT series from Würth Elektronik actually makes it easier than ever to implement discrete SiC gate driver designs. These off-the-shelf components are compact surface mount transformers that have been optimized for silicon carbide applications. With extremely low inner winding capacitance, the AGDT helps achieve higher common mode transient immunity, or CMTI. And then finally, we'll talk about the characteristics of DC link capacitors placed between a DC source and a power stage, such as an inverter or a motor drive, and this helps to provide temporary buffer of energy. We'll also discuss the advantages of the Würth Elektronik polypropylene film DC link capacitors.
So I will start with this, normally a short introduction about myself. I'm Didier Baloco. I have an engineering degree from the École nationale supérieure d'électronique de radioélectricité de Bordeaux in France in 1992, and a PhD degree in power electronics in the same University of Bordeaux in 1997. Then I joined a company in telecom in France to do some research about DC-DC, AC-DC, and DC-AC converter, very applied research from in a range of 1 watt to 150 kilowatt, and I did that until 2014. Then I became a FAE for Fairchild, supporting south of France and Spain and Portugal. And with the merge in 2016 between Fairchild and onsemi, I joined onsemi, and in 2018 I take the opportunity to move as a business marketing engineer, supporting EMEA for industrial application. So let's start the session today with this 25 fast EV charging reference design using silicon carbide module. So I will do a quick introduction, review the key building blocks like the six-pack and the NPC, the DC-DC, dual active bridge, LLC, and so on. Then we will do a 25 kilowatt building block review. I will explain you why we decide to use module and identify all socket or part that you can get from onsemi portfolio. I will leave to Wurth to identify their products in that application. I will show you some measurement and result and then conclude my talk. So let's start with the building blocks that you have available to make such a high power stage. You can see here, I divide the screen in the upper level where you have the three-phase active front end, the six-pack boost, TNPC, NPC boost, or Vienna topology, and on the lower part of the slide, the isolated DC-DC that can be also NPC based or neutral clamp based half bridge or full bridges. There's the dual active bridge topology that's very interesting because it's bidirectional, and the LLC or CLLC, and for the LLC, CLLC, or dual active bridge, depending on the voltage, you can stack those topology to handle higher input-output voltage. For those various solutions, for example, the Vienna or the six-pack converter as shown here, we can use either module or discrete silicon carbide diode and silicon carbide MOSFET. And for each topology, we have module with dedicated layout for that topology. The same go with the bidirectional TNPC version. We have either a module or discrete diode and MOSFET available, and they can be used directly. For the DC-DC isolated stage, this is the same. We are mainly here using 2-pack or 4-pack module, or discrete also diode and MOSFET can be used, depend on the voltage and the current. So in our 25 kilowatt application, we have those two power blocks that we can see on the upper of this block diagram. We have the AC-DC 3-phase 2-level boost and the DC-DC bridge on the top. And all the orange block, it's block where onsemi can provide you components. We have the voltage sensor, current sensor, gate drive, isolation, EEPROM, connectivity, and also the auxiliary supply and the ground fault protection. All of that can be found inside onsemi portfolio. To build a fast DC charger, we use block. And block from 12 to 75 kilowatt. And here we have chosen to make a 25 kilowatt block. And we parallel those blocks to get 100, 200, or 300 kilowatts. On top of that block, when we stack them, we connect them from, they have the same input and share the same output. And to manage them, we have a user interface with connectivity and controller that will dialogue with the car and with the block to set the output power or the output voltage that the battery in the car need. So the complete charger has been made to be compatible with the European or the US line, 400 or 480 volt AC, maximum input current 40 amp, accommodate with the 60 or 50 hertz grid, and the output voltage will be in the range of 200 volt and 1000 volt with a maximum output of 50 amp. We have integrated all the protection over voltage, over current, under voltage, DSAT on the driver. We have many interface also for connectivity like SPI, A2C, UART, USB. We limit the operating range from 0 to 40 amp, and we're willing to make a full bidirectional device. The other parameters are here as a guideline. So we divide the building block in two boards. One is the 6-pack boost AC-DC, and the second one is the dual active grid DC-DC to be fully bidirectional. And you can see here the 3D view of the boards. For the output characteristic, I told you we are in the range from 200 to 1000 volt and with a maximum of 50 amp and a maximum power of 25 kilowatt. That means that below 500 volts, we will operate at constant output power with 25 kilowatt, and the current will at below 500 volt, the output current will be constant, and we will operate with an output current of about 25, 26 amp. And then above 500 volt, we will operate with constant power, 25 kilowatt, and we'll get to that point. So the products available inside onsemi portfolio, they are pointed here. You can see we have the inrush control with MOSFET. We have the voltage sensor, the 3 module for the 3 half bridges, the gate drivers, the auxiliary supply, and we use a common control board that has been developed for motor control. Here you have the list of those devices, and you can see the 10 milliohm 1200 volt module on top, and the NCD5700 as a gate driver. You have the list of the voltage amplifier, current amplifier, and so on, the digital isolator. And for the auxiliary supply, we use two boards. One board for the high voltage to medium voltage 15 volt conversion, and then from 15 volt to the various voltage needed, we use a special board to get the 20 and -5 volts for the gate driver. The DC-DC block is almost the same, except we have less module. We have reused most of the devices used for the PFC with the same control board, the same auxiliary board, the same op-amp, the same gate driver, the same isolation barrier. So we found almost the same part list on the bottom, except on the top, the number of modules has been reduced, and so the number of gate driver is not the same because we don't have the same number of components. So why using module? First of all, because module, we can carry much more power. And with module, you see that using F1 size, for example, we can scale the power from 6 to 25 kilowatt. And using F2, the big one, we can go to 50 kilowatt and up to 75 kilowatt with this module. Gate driver, we use the NCD5730, that is an isolated gate driver that offer very good propagation delay below 15 nanoseconds and very good delay matching, also lower than 10 nanoseconds. He has a low output impedance, drive capability from 4 to amp and -6 amp sync, 25 volt output range, that's very good for silicon carbide, very good voltage immunity, 100 volt per nanosecond, minor clap, DSAT function, and an isolation capability of 5 kilovolt RMS and 8 millimeter cleavage. This part, we have released now the 57100, that is the same pinout, same features, except we have extended the VDD minus VEE range up to 32 volt to be even more compatible with silicon carbide, and we have included a DSAT diagnostic function that we have a patent pending. The auxiliary supply socket is made with, we use 3 auxiliary supply, one for the AC-DC and 2 for the DC-DC, one on the primary side, one on the secondary side, because if we start operate the product reverse, we need on the secondary side and also an auxiliary supply that will start and give the information to the primary side because we're operating a reverse. Those high voltage board 40 watt, 15 volt out are made, as you see, it's a simple flyback schematic with a silicon, sorry for that, with a silicon driver that normally drives silicon MOSFET, but here we drive the silicon carbide directly, even if it's not optimum in terms of gate voltage, but that's enough for 40 watt. The full power list of this board is available on this slide, and you can see that for 1000 volt input, 100 volt reflected voltage, we have with 1200 volt MOSFET, we have only 100 volt headroom. But if you use the new 17 volt 1 ohm silicon carbide MOSFET, you can get much more headroom and much more balanced transformer ratio. Amplifier for voltage and current, we have a schematic that we can provide you for voltage and current sensing that has been proven in our lab, and we have reused those schematics for voltage sensing based on the NCS333 series, and for current sensing based on the NCS210 series that is already integrated the voltage, the resistor for the voltage amplifier, and they are matched. And in this way, we can get very accurate gain and very high signal differential mode ratio rejection. We have the same schematic also for LEM sensor based on the voltage amplifier, the NCS333. measurement and result now. For avoiding losing all the power, we made a loop testing, meaning that the output voltage is fed back to the input and so to the grid, and then so recycle inside this loop, and the grid only need to produce the energy for the losses inside the loop. And in this way, to test the 25 kilowatt system, we only need 1.5 kilowatt that correspond to 500 watt per board losses around at full power, in full power mode. And it all allows us to test also the bidirectionality of the devices. Here we have the input voltage and current. You can see that on the right side, when the voltage and current are on the same scale, they are almost impossible to determine which one is which, meaning that we have a very good power factor and very low THD. Here, this is the efficiency of the AC/DC, the active front end. Our goal was to have an efficiency above 98% at full power, 25 kilowatt. We are around 98.2 at maximum input voltage and maximum power. The dual active bridge also reached 98%. You can see here, depending on the input and output voltage, we are above or very close to 98%. Sure, having lower input and output voltage makes things more complicated in terms of for the efficiency. Some people say that DSAT function is not needed for silicon carbide, and here we had, as we use an IGBT driver, we had the function, and we could use the DSAT function as a protection. And as you can see on those graphs here, the DSAT function is working properly and can be set for silicon carbide also. As a conclusion, various high power topology can be used for fast EV charger. For that power level, modules are the best way to go. We have more than 20 blocks that we can address with our onsemi portfolio. We have the module for sure, the gate driver, the voltage and current, our operational amplifier, the isolator for digital signal, the auxiliary supply that includes many parameters, and the communication interface also. If you need more information about this topic, you have a dedicated landing page that we create during the development of this 25 kilowatt SiC-based fast DC charger. And you have also a dedicated EV charging landing page. You have the two links on this slide.
Hello, everyone, and welcome from my side as well. My name is Octavian Stroh. I'm a product definition engineer for Würth Elektronik, and I'm supporting the entire Eastern Europe. As a product definition engineer, my main job is to support application engineer from different IC houses or IC manufacturers, however you want to call them, who are working on reference designs, demo boards, evaluation boards, in choosing the right component for their design. Also, I'm supporting with layout reviews, schematic reviews, and I can help application engineers to design filters for passing the electromagnetic compatibility tests. As a background, my experience is in power and audio electronics, design and testing, high voltage, high current, buck POL converters, PCB layout design, 3D design. And since 2022, since April to be more precise, I'm a product definition engineer at Würth Elektronik. Today on the agenda, we're going to discuss about two main topics. We're going to talk about the auxiliary gate drive transformers and the flat wire power fraction correction choke with examples of how they were integrated in onsemi's 25 kilowatts ultra fast charger. And I'm going to give you also an overview of the different part numbers and the main characteristics of those parts. And I'll also be diving into a bit of more important technical aspects, so to say, regarding the use of our auxiliary gate drive transformers and the technical considerations behind why we chose to go with a flat wire for our PFC chokes. So first of all, I will start by introducing our extended AGDT. This stands for Auxiliary Gate Drive Transformers. The AGDT series is specifically designed to provide ultra-low interwinding capacitance and rugged isolation for implementing isolated auxiliary power supplies that drive the gate driving ICs. Those parts feature wide input voltages, so from 6 to 36 volts. In this case, up to 6 watts of power, which can be extended up to 10 watts with an EP10 package. And they also feature very important ultra-low interwinding capacitance down to 1 picofarads, which help with the common mode transient immunity, and it can also help with EMI performance. It's also worth noting and specifying that our parts are AEC Q200 qualified. Currently, we have extended the series with 8 different parts. Now we have a total of, if I remember correctly, 14 part numbers, which are all available on our in our online catalog. There's absolutely no minimum order quantity. If you want to get some samples to try them out, you can even order one, so that's fine. And they're also available in our online simulation platform called Red Expert, where you can find different reference designs with these parts. Here we have the 25 kilowatts reference design, ultra-fast charger reference design from onsemi. We have the 3-phase rectifier and power factor correction, and we have the dual active bridge converter. Now, for the PFC stage, we have 10 instances of the SECO LV-DC-DC evaluation board, which contains our AGDT, auxiliary gate drive transformers. The output voltages actually for these evaluation boards are plus 20 volts, plus 5, and minus 5 volts. Out of these 10 boards, 6 are used to drive to power the stick gate driving ICs, and the rest of them are used for isolation to power the ADCs and isolate the ADCs that measure the current and voltage, and also to power the ICs that take care of the lock communication and CAN communication. For the dual active bridge, there are 12 instances where these boards are used. 8 of these auxiliary gate drive transformer are used in the primary and the secondary side. So we have 4 in the primary, 4 in the secondary side for the to power up the ICs that drive the gates of the SiC devices. And the rest of 4 boards are used to isolate the ADC interfaces that take care of the current and voltage measurements in the primary side and the secondary side, and also to power the ICs used for communication. So this is where the parts are used, as I mentioned. So 6 in the primary, 6 on the PFC board, and then 12 totaling in the dual active bridge. Next one. So a bit about the gate drive transformers. We have applications like silicon carbide or gallium nitride, like high voltage semiconductor basically, that under hard switching operation, we need galvanic isolation, which is a common requirement for safety and functional reasons. And also depending on the application, it might require basic or reinforced isolation. Now, we have operating voltage, insulation material, we have pollution degree, and also different applicable regulatory standards that set the minimum creepage and clearance distances, as well as the required dielectric voltage requirements. And this affects the components we can use for this across this isolation barrier. The isolated gate drive IC and the transformers, both of them bridge this isolation barrier, thus having to meet very stringent safety and functional requirements. We know that each SiC, silicon carbide or gallium nitride FET would require independent gate driving stages with their own isolated auxiliary supplies. This not only enables to individually control each of the device, but it also helps to keep the gate current loop small and local, so small and local to the device itself, minimizing the adverse effects of the parasitic loop inductances and ground bounce, which can cause very high DI over DTs, and which can, in consequence, cause EMC problems. With the auxiliary gate drive transformers, we're able to build two different kinds of supplies. We can have isolated supplies, bipolar or unipolar. If the silicon carbide device requires a negative voltage, the typical auxiliary power supply will look like the one in the figure here. So it will be a bipolar one because it will require a negative voltage as well to turn the silicon carbide off. It's also important to notice the fact that some silicon carbide devices, they feature an additional Kelvin pin for the source terminal, as shown in this image here. This connection provides a dedicated gate source path for the gate drive current, which is not shared with the current in the power loop. So next one. Also, a typical application is unipolar auxiliary power supplies. This can be used for devices or power modules that do not require a negative voltage, and therefore we have different AGDT part numbers with only one secondary for implementing a unipolar auxiliary power supplies. We have the same type of Kelvin connection approach, which should be used in this instance as well. We should be connected as shown in the image. Now, I mentioned before low interwinding capacitance and why it does matter. We have something called CMTI. CMTI is an acronym that stands for Common Mode Transient Immunity. This is usually measured either in kilovolts per microsecond or in volts per nanosecond. And this is an indication of the maximum rate of change of voltage, dV over dt, which can be tolerated across this isolation barrier. And this is the maximum voltage that can be tolerated before malfunction can occur, causing loss of the control of the SiC device and very erratic behavior of the whole system. So this CMTI, Common Mode Transient Immunity rating, directly depends on the parasitic capacitance value that we have across this isolation barrier. And to this parasitic capacitance, we have two contributors. We have the isolated IC and we have the AGDT transformer. Now, I'd like to introduce to you our newest series, the Wurth PFC. The design of this series started almost at the same time as the development of the 25 kilowatts ultra-fast charger, and it was tuned and specified in accordance to the needs of such a demanding application. From this, more part numbers were derived, and we now have a total of 17 parts in stock, which will be released, as far as I know, in the middle of May. Also, there is no minimum order quantity required for this part. For this design, we have chosen flat wire for the windings because we wanted to target the efficiencies associated with the high current and high switching speeds. Also, we chose them from mechanical standpoints because flat wire is more rugged, considering the size and the weight of such a choke. This table shows an overview of all of the part numbers that will be released soon, along with the typical inductance values, DCR. We have rated current and saturation current. Please note that due to the winding style of the flat wire, there are some gap between the turns, which allows us to have higher currents with air cooling. That's why we also specify the rated current at different values of air cooling. Here we have again the 25 kilowatts ultra fast charger, this time only the PFC stage, because this is where our part numbers are used. We have 3 part numbers used here. The value of the inductance is almost 180 microhenries with a saturation current of 105 amps. It's a 3-phase input, so 3 power factor correction chokes are used. Please note that the parts shown in the image here are just the initial samples that were sent to the application engineer for validation purposes and for prototyping. And the final version of the series will not be featuring flying leads, but direct through-hole mounting and a central screw for mechanical stability. Also, this direct connection helps with optimizing the EMC. Here is the block diagram, again, to help localize the position of the 3 power factor correction chokes. And now, a bit of theory to help us understand at the end why we chose to go with flat wire, because that is the most interesting part. So we're going to talk a bit about skin effect. So what is skin effect? It represents the tendency of the density of the current density in alternating current to become distributed towards the surface or the skin of a conductor. So therefore, with higher switching frequencies, the more the current density will be pushed towards the surface. Or we can say that the higher switching frequency is, the less of the conductor's cross section is used to carry the current. This is shown in the image here for different frequencies. So depending on the frequency, the higher we go in frequencies, the less we use from the conductor. This creates increased AC resistance. And this happens because we can see in the image to the right, as the current passes through the conductor, it generates a magnetic field, H, that induces circulating eddy currents inside the conductor. Now, if you look closely at the direction of these eddy currents, you'll notice that they cancel some of the main current that pass through the conductor, through the center of the conductor, and reinforces the current to the sides, so to the skin, close to the outer surface. Now, a bit about the proximity effect. The easiest way to visualize it and explain it, we have in this image 2 conductors running in parallel. They both are carrying alternating current. Those currents pass through the conductors that, because they're alternating currents, they will generate a time-varying magnetic field. Again, this magnetic field will induce circulating eddy currents from one conductor to the other. Those eddy currents, as they are induced, they will increase the current density to the sides and decrease it to the sides closest to each other. So on the opposite sides, we will have increased current, and on the sides closest to each other, we'll have decreased current. This happens if the 2 conductors are carrying alternating current in the same direction. If they carry it in opposite direction, the concentration of the current will happen on the surfaces closest to each other, so here. This again, it will create the same thing as the skin effect. So it will increase the AC resistance, and we will see a higher increase in AC resistance as we go with higher frequencies. Now, to test some of our theories, we created 2 samples. So we selected a standard flat wire part number, the image on the right. And what we did, we used the same core, and we wound with a round wire to create the same inductance. We chose the wire gauge to be so that it can handle the same amount of current as the flat wire, in such a way that it also creates a similar DCR. Now, from the measurements, we noticed 2 things. We have 27.7 milliohms for the round wire of DCR and 27.1 milliohms for the flat wire. It's just a tiny, you might call it, 0.6 milliohm difference in DCR, but where the biggest difference is in the interwinding capacitance. 154 picofarads for the round wire inductor sample, and only 3 picofarads for the flat wire sample. Now, with a round wire, the windings in most cases will be done with different numbers of layers. Looking at the two images, we can immediately expect some problems, and here as well. So we can clearly see that with more than one layer, they will have parasitic capacitance between wires in different layers, and also between wires in the same layer in the horizontal axis. This will form series and parallel parasitic capacitances, which will create a higher value of parasitic capacitance compared to the one below, which represents the flat wire windings, which we can see that there are only series connected parasitic capacitances. What it means that in the end, the total parasitic capacitances will be smaller because they are series connected. So just to give you an idea, let's say we take those two samples that we built. They're around 200 microhenries of inductance. And let's go with the 150 picofarads of parasitic capacitance for the round wire. If you would calculate it, this means that the self-resonance of this inductor right here is 1 megahertz. Now, with the flat wire, we are down to 3 picofarads. Down to 3 picofarads, if you calculate it, the resonant point will be around 6.5 megahertz. So, the higher the resonance, it means that we'll have a wider frequency spectrum where the part is acting like an inductor, because as with any inductor, actually, after the resonant points, we go into the capacitive region. So therefore, with higher resonant frequencies, we are able to operate the inductor also at higher switching frequencies. Continuing with information extraction from our measurements, we will now have a look at the temperature increase between the round wire sample and the flat wire sample. With just 15 amps of current, we can already notice a difference of 14 kelvins. Remember that we had 0.6 milliohms difference in the DCR, but this will not create by itself that huge difference. Where the temperature difference is coming from actually is from the better heat dissipation capabilities of the flat wire due to the increased surface area. Of course, let's say we take one of our part numbers, which has a saturation current of 105 amps, and you put a peak current of 105 amps through that one, the temperature difference will be much higher because we will also gain contribution from the increased power losses. We also ran a AC resistance measurement to compare the two different samples, the one with the round wire and the one with the flat wire. And we can see that there's not a huge difference up to 250 kilohertz of switching frequency. And it shows kind of a linear increase. After 250 kilohertz, when the skin and the proximity effects start to be dominant, we can see there is a clear difference between the flat wire and the round wire, with the round wire showing almost an exponential increase in the AC resistance. We can see that the maximum differences in AC resistance is, so we have 8 ohms for the flat wire and 22 ohms for the round wire. So, still wondering why a flat wire? Well, we have lower DC losses because we have a lower DC resistance. We can reduce the skin and we can reduce the proximity effects. Therefore, we reduce the AC losses. Also, with the flat wire style, we also achieve lower interwinding capacitance, which allows for a higher switching frequency. Also, with the flat wire, we have better mechanical stability. Therefore, we increase the ruggedness of the coil's mounting system. Now, the image on the right represents a real equivalent circuit of an inductor. So we have our R1, which is the DC resistance, which we lowered. So that's a tick. We have our capacitive region, We have our inductive region right here, and we have our resonant region. We will set aside the resonant region for now and only focus on the capacitive and the inductive region. As you can see, these are in parallel, and reducing the magnitude of certain elements in here will have a big impact in the efficiency and the performance of our choke. So we have R2, which is our AC resistance, which we have lowered. And with a decrease in, we have lowered with a decrease in skin and proximity effect. Now, the lower the interwinding capacitance means we are reducing C1 here. And this moves our capacitive regions of the choke to higher frequencies. So every box is ticked, which means the flat wire is a clear winner.
Welcome. Thanks, Octavian, from my side. And yeah, I'm going to try to be fast and quick. And then maybe we'll have more time for questions. So a couple of words about me. My name is John Itzque Rodriguez, and I have been working in the capacitor division of Würth Elektronik for more than 4 years. And I take care of some technical aspects regarding the applications and the use of capacitors in general, as well as measurements and simulation and red expert. Let me check one. Okay. Yep. So in this presentation, I will briefly present the new VCAP FTDB family of DC link film capacitors. And yeah, since the presentation is very short, there's no point in explaining the agenda. So let's go. We'll start introducing the capacitors. So we released this family in November last year, but of course we have been working on these components for a long time. The VCAP FTTB series are specially designed for DC link applications. So you can find them already in our online catalog and also in Red Expert. We have 24 standard parts in the catalog, which are always available from our central warehouse from stock. And we have rated voltages from 500 volts to 1.2 kilovolt and capacitance between 1 and 75 microfarad. So the term NKP, which was part of the series, means that the capacitor is made with metallized polypropylene film. So this is the plastic film acting as a dielectric, and we can deposit or with one metallization in a side. A thin layer of aluminum is deposited on one side of the dielectric, and we form the electrode. So two films like this are rolled together, and we create this kind of capacitors. So polypropylene materials provide very stable capacitance characteristics, as well as very long life and self-healing properties against the holes that are created inside of the dielectric when you have a surge voltage. So the capacitors in this series are quite big, and most of them have 4 terminals for a better mechanical ruggedness as well as current capabilities. So here we have the reference design from onsemi again. Since we were involved at the design phase of the project, we could offer the capacitors that best fulfill their needs. In this case, for the PFC output, we have a 800 volt bus. So they selected a capacitor with 75 microfarad and 900 volt of rated voltage, and they placed one capacitor in the output of each PFC power stage leg, so 3 in total. And we have the same capacitor 2 times in parallel at the primary side of the converter, which is the same bus. We can consider that all of these 5 parts form together the DC link capacitance between one power stage and the other. So finally, at the secondary side of the DC-DC converter, we have two capacitors of 50 microfarad and a rated voltage of 1.1 kilovolt. So these ones are there to allow the maximum output voltage of the full system, which is 900 volt. So if we look at the block diagram, we have the 5 capacitors rated for 900 volt here, and on both sides of the same DC link connection, as I said, and in the secondary side, we have the 2 capacitors, which in theory are connected to the battery. So of course, DC link only means the placement of the capacitors. So now in theory, we can be using any type of capacitor here, but with the amount of power handled by this application, we can only consider either film capacitors or aluminum electrolytic capacitors. So both technologies are valid, and each case must be carefully considered because we have advantages and disadvantages. So it's a complicated comparison. So let's see carefully. So of course, the rated voltage is a huge factor. So here we can use the advantage of the silicon carbide module, and in this application, no single electrolytic cells are able to work with this high voltage. So a series connection of ECAPs is possible, but of course it will increase the part count and complexity because some balancing may be required. So due to the very low ESR, polypropylene film capacitors can handle a very large ripple current. So in comparison with relatively high series resistance of the electrolytic caps. So on the other hand, for the same size, electrolytic capacitor cells offer or provide many times higher capacitance in the same volume. So either you have capacitance or current capability. So the consequence of this is that we really need a low ripple voltage on that DC bus. If we really need the low ripple voltage, we might not get enough capacitance by adding film capacitors. So we might need to use electrolytic capacitors. Finally, let me remind you that the ECAPs have a liquid electrolyte that will dry with time, and the lifetime is heavily dependent on temperature. So another advantage of film capacitors is that the lifetime, both on load and on storage, is very long, even at high operating temperature. Now, let me look into detail of the specification of the ripple current limitation, which I mentioned before. So this is a capture of the datasheet of the same capacitor I mentioned before, the 75 microfarad 900 volt, and you can see marked the ripple current specification. So in the datasheet, we have written that we defined the electrical properties at 20 degrees, so as laboratory conditions. But in operation, there is ripple current, and due to ESR, the ripple current will create some self-heating, and we have to limit this self-heating to a maximum of 15 degrees. So if you look again, we have 70 degrees as in the definition of maximum ripple current of 25 amps RMS. So we expect a self-heating of 15 degrees. And with it, we will arrive at the 85 degrees Celsius, where the rest of the parameters are varied. So as I said before, for temperatures higher than 85 degrees, some specification will change. So you can see these graphs in the datasheet for clarification, and you can see here, for example, in the left, the voltage rating applies up to 85 degrees Celsius, and in the right, you can see the current rating applies up to 70 degrees. So to take into account that self-heating at maximum river current. So by now, my colleague already spoke about Red Expert, and I just want to remind you, we also have a module about DC-link capacitors. We offer a detailed grid table to filter and compare between the different parts of the series, as well as we offer a range of measurements like the impedance versus frequency, ESR versus frequency, or also very interesting, the temperature dependency of capacitance and also dissipation factor. So before I finish, I want to remind you that the catalog is just the starting point. As I said before, we have 24 part numbers in the online catalog, and these parts can be ordered at any quantity because we have stock. We have them in stock. Also, we offer free samples as well as measurements of in-red expert and libraries for CAD program and simulation programs. But these capacitors are quite big, so we understand that it is essential that the parts suit your application perfectly. So for this aspect, we for different demands, we offer additional components as customer-specific solution, which means that the orders must be above the MOQ, so a minimal order of quantity. So we, it's not a huge quantity, but this is parts that we don't have in stock. So this is a short summary of the general limitation of what we offer. So since we don't have a stock of these parts, we can only provide measurements and other support after we produce the order quantity. And finally, for the designing process, we have provided in the past some special testing parts, like what you can see in this image, which has 2 thermocouple temperature sensors inside of the package. So if you need something like this and you think it's doable, don't hesitate and ask your sales contact person or the capacitor team directly at this address that you can see on the screen, which is cap hotline at ve online, ve-online.de. So finally, I want to direct you to some other resources that you can have in case you want to know more about this topic. Of course, you have an email to ask any question you might have about capacitors, of course. So regarding this topic of DC-link capacitors, I made a longer webinar last year with the title DC-link capacitors specification and application. So you can find the recording in YouTube, and it lasts about 40 minutes, and I go into detail about the specifications, and also I do a longer comparison in one specific case for the alternative electrolytic capacitor or DC-link solution. Since we are already talking about polypropylene film capacitors, another webinar from last year, I talked about harsh conditions, and especially film capacitors, which are quite sensitive to the air humidity, which can be critical in combination with high temperature condition.
You can find the entire line of Würth Elektronik capacitors, transformers, chokes, and also electromechanical components available at Würth Elektronik online. And for any questions any time of day, click the chat icon to talk with a live team member. You're listening to Würth Elektronik's What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Elektronik technical specialists who are going to shine a light on our topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Würth Elektronik's What's Up podcast.